Hey everybody, welcome to 11H, gravitational force and Newton's third law, though I don't know why they call it a Newton's third law because it doesn't come up in this problem at all. So it says in the four cases shown below, two spheres are in contact with each other, somewhere in space far from the influence of other objects. The spheres have radii shown in each diagram. In each case, the two spheres exert a gravitational force on each other. Okay, we're going to come back to this picture in just a moment here. So next thing we have here, it says in part A, consider all given cases and assume all the spheres have the same mass, capital M. That makes things nice and easy. Let the left sphere have a radius R1 and the right sphere have a radius R2. Write an equation for the gravitational force F that the two spheres exert on each other that could apply to any scenario above. Your equation should contain M1, M2, R1, and R2 and physical constants as appropriate. Okay, so the gravitational force is going to follow Newton's universal law of gravitation, and that says that the force of gravity is the gravitational constant times mass 1 times mass 2 divided by the distance between their centers squared. Now that distance is just a generic distance for now. So let's set it up a bit more specific for the problem here. So mass 1 and mass 2, that won't change, but the distance between their centers at any given point will be this radii plus that radii. So we got to go from the center of one all the way to the center of the other one. And so when we go to write this, we'll put in parentheses here R1 plus R2, all of that squared. Now in this particular case, they said include M1 and M2. They also said the masses are just M, so you could like get rid of those subscripts or make it M squared, but we'll just keep it just like that for now. All right, so now moving on to the next part here. They say rank the cases by gravitational force that the spheres exert on each other, assuming that all the spheres have the same mass, include greater than, less than, or equal to, clarify your rankings. Okay, so we need to rank them. So let's go back to this picture here for a second and look at this. So the distances are going to be the only thing that's important because the masses are all the same. So if we go R to here and R to here, then that is 2R. So from the center of one to the other is R, and same thing there. So the distance between their centers in that case is 2R. Here we go 2R and then another 2R to get to the center of that one. So the distances between their centers is 4R. Here we go 3R and then R to get from one center to the other. So this distance is also 4R. And then here we go 3R and then 2R to get from one center to the other. So this distance between their centers is 5R. So we'll sort of keep that in mind now when we go to rank the different strengths here. So it says use your equation from part A to explain how you made it. Well, in that case, the only thing that matters, since the gravitational force never changes and their masses are all the same, all we need to do is look at the distances, their radii added up. The bigger the distance added up of their radii, that's down in the denominator. So the bigger the distance, the less force. So if we look here, then we can see that case A is the closest. Case B and C are next and they're tied, and case D is the weakest there. So when we go to rank these, the strongest force will be A. That is greater than B and C, which are equal to each other, and the furthest away, and therefore the weakest, is case D there. All right, now moving on to part B, in the last part here. It says the four figures show two identical planets with radius R. Their centers are separated by a distance of 4R. Okay, so that means from here to here is 4R, and an R is here, and another R is here, which means the distance between here and here is 2R between their surfaces there. They are near each other but not colliding because they are orbiting each other. An astronaut stands on one of the labeled positions. Rank the magnitudes of the net gravitational force. So magnitudes, we don't care about which way here. On the astronaut at each of the four labeled positions from greatest to least. Okay, kind of like what we did before. Well, here, when we stand on this side, on part A, this planet is going to pull on it. By the way, no matter where you're standing, A, B, C, or D, one of the forces, let's just call that the force of gravity, is going to be equal to that mass times of the planet So g times the mass of the planet times the mass of the person over the radius squared. And that never changes. That's the same no matter where you stay. So the other thing is basically what's going on with the other planet. So as we stand on A, planet 1's going to exert a certain force. Planet 2's over here, but here's the key thing. When you're at A, you're going to have a pull to the right from planet 1, and you're going to have some pull also to the right from planet 2. It's going to be weaker because it's further away, but whatever that is, they add up to each other. The same thing is going to happen over here at position D. So if you're standing at D, you're going to have a pull from your planet, but you're also going to have a pull from the other planet in the same direction. It's going to be weaker, but in the same direction, so they're going to add since they're both to the left of you there. However, when you stand, let's say, at position B, planet 1 will pull you to the left, and planet 2 will pull you to the right here. And so that pull will be weaker because it's further away, but they will be fighting each other as opposed to adding together over here. And then the same thing at C. Planet 2 would pull you to the right, but planet 1 would pull you to the left there. They're fighting each other. So since A and D, the forces add together, then you're going to have the force at A is equal to the force at D. And those are greater than the force at B, which is equal to the force at C. Again, at A and D, the pulls of the two planets add together because they're in the same direction. And at B and C, you have this fighting going on. And so they're going to be canceling each other out a little bit and weakening each other. And situations are equivalent at B and C. You're R away from your own planet and you're 2R, or 3R away, sorry, this 2R plus that R away from the other planet.